Hello, this is Dr. Mohammed, and this is another video under Dynamics of Structures. And still we are under the main title of Multi-Degree of Freedom Systems, MDOF. And today I'm going to talk about or give an example, work out an example, very important example on natural frequencies and mode shapes. So we're going to discuss about how we can obtain natural frequencies and mode shapes, and how we can understand what we have explained in the previous lecture. So I think that this lecture is very important if you want to have a very good introduction to multi-degree freedom system. The previous video and this video is going to give you a very good exposure to multi-degree freedom system in general. Okay, let's jump now directly to the example that we are going to have for today, and let's read it like word by word, because sometimes reading the example itself is giving to us some key important understanding for the entire problem. So this example is an RC. It is reinforced concrete frame as shown, as you can see it here. So it's frame, RC frame, and it is 4-meter span, 2 floors, and the height of the floor is 3 meters, and there is distributed load on each floor with the amount of 30 kilonewton per meter each. And we are going to find that this building or this frame is having concentrated masses, as we can see here, on the floors. Okay, so this is in general what this frame is all about. It's composed of 2 stories. So the word 2 here, the meaning of 2, it means that we are talking about 2 degrees of freedom system, 2 stories. Okay, but still maybe we are not sure now whether the masses are going to be concentrated and lumped at each floor, or we are going to have some masses that is related to the columns. Okay, so we need to understand it from the examples. Each floor carries a load of 30 kilonewton per meter. This means that it is distributed load, and take care, this is considered to be loading, like weight, for example. Whenever we are dealing with our problem, we need to work with masses. This means that there is gravitational acceleration as involved here. Okay, inertia of columns in each story is equivalent to that of cross-section of 0.5 by 0.5 meter. This means that the whole columns, okay, in each story is equivalent to a cross-section of 0.5 by 0.5, 0.5 by 0.5 meter, as if this column and this column, both of them, if we are going to put them together, they are going to have the equivalency in stiffness as we, or if we put one column only, like this, and the cross section of this column is going to have 0.5 by 0.5 dimensions. Okay, so now we can understand this. This means that we can put our system as you can see here, Okay. After that, assume the column to be weightless and the girders to be rigid. So number 1, columns are going to be weightless. Okay, columns are going to be weightless. Means that the columns are going to have no mass contribution to our system. So these columns are going to have no mass contribution. So the masses involved with the column, it is neglected. This means that we are going to get closer to the understanding that each floor is going to have the lumped mass, and the remaining part of the system is not having mass that should be considered. So assume the column to be weightless. Okay, weightless. And girders to be rigid. The meaning of girders to be rigid means that, as I have mentioned before, that it means that this is the girder which is having high stiffness, okay, compared to the column. This means that whenever the girder is going to move laterally, okay, what will happen? That the column is going to have this shape. This means that always the angle between the horizontal girder and the vertical column, or the this column after moving laterally, it is going to be 90 degrees. This qualifies our system to be exactly shear building. Shear building. And this is one of the most important conditions for the shear building, okay? That girders needs to be rigid. So we are reading each word in the example with great care in order to understand everything of it. So, okay, we understood now what is the meaning of weightless and what is the meaning of to be rigid, the girders to be rigid. Okay, now let's see what the example needs. Determine the natural frequencies and the mode shapes for the frame. So we have two things here, or we need, or the example requires two things. First, the natural frequencies, and number two, the mode shapes of the frame. Okay, and take Young's modulus of concrete to be 20,000 megapascal. This is given in the example. Okay, so up till now I think that it's okay, no problem at all for us, and we can go to the next part, which is related to the solution itself, and see how we are going to solve our problem. First of all, we need to think about some issues here, as I have mentioned before. First of all, regarding the column, it is weightless. This means that only floor masses are considered, and we are talking, or we are going to consider lumped mass. And as we said, girders, they are rigid. This means that shear building concept applies. Okay. And when we were looking to the figure of the example, we have two stories, right? This means that we have 2 degrees of freedom. 2 degrees of freedom. This implies that we are having two different frequencies, natural frequencies. And I'm going to explain about what is the meaning of two natural frequencies here toward the end of the solution. Okay, but now we understand that we have 2 degrees of freedom, 2 coordinates that the mass can go, and 2 coordinates that we want to observe or monitor or record or report the displacement on the floor or on this frame at these 2 different degrees of freedom, or add these different coordinates. And number 2 is mode shapes are 2. So we have 2 mode shapes. Okay, as we're going to see, we are going to have 2 mode shapes, one like this, for example, and the other one is going to be something like this, as we are going to explain later. So this is the meaning of 2 degrees of freedom, 2 floors. And also this implies that our stiffness matrix and mass matrix, okay, both of them, they are going to be with the dimensions 2 by 2. So we have 2 rows and 2 columns. This is what we can get from the example wording. Okay, now let's go next, and let's go to see what are the steps of solution for us. What are the steps of solution for us? First of all, we need to remember that we need to put a strategy for the solution. Number 1, we need to obtain the stiffness matrix and the mass matrix. So we need to put, or to know, what are the elements of the stiffness matrix and the mass matrix. And after that, the second step, as we have explained in the previous video, we are going to obtain the natural frequencies from the famous equation that I have explained last video. If you couldn't understand this equation, then please pause the video and revisit the previous video. Simply, we went through this derivation and we said that at the end we need to obtain the determinant of this two matrices that is being subtracted from one another, the stiffness matrix minus omega squared times the mass matrix, equal to 0. When we are going to equate this determinant with 0, we are going to have a polynomial, and this polynomial is going to be in omega squared. We're going to solve it using the quadratic equation law, and then we're going to obtain some roots. These roots, in our case, we're going to find it is going to be given us two different roots, omega 1 and omega 2, because we have 2 degrees of freedom. After that, this is step number 2. After that, step number 3 is we need to obtain the mode shapes. The mode shapes, which means that what are the different shapes that our structure is going to have when it is going to be under motion. So we're going to assume that, for example, it is going to move in this way, other way it is going to move, or other shape it is going to be in this way. This is what we call it the mode shapes. Means that what are the expected shapes or mode shapes, okay, that is going to be experienced by our system, okay, under free vibration. Okay, it is under free vibration. So based on that, we need to know how much this amplitude is and how much this amplitude is, right? So this is, let's assume this is A1 and, sorry, this is A2, and this is A1, for example, which is the amplitude at the second floor, the amplitude at the first floor. This can be, we can put it like this, which is A1, A2, and we say that this one is the mode shape, the first mode shape, which is, I put it here, first mode shape. Similarly, we are going to find for this one, for example, it is going to be the second mode shape, another way or another form of motion that we are expecting under free vibration of our system. Okay, so at the end, let's clean everything. At the end, we need to obtain frequencies, which is going to be omega 1 and omega 2, and each frequency is going to have conjugate or associated mode shape. Let's assume A1, A2, and here it is going to be another A1, A2. Okay, they are different. This is omega 1. Let's assume this is, for example, or this is the mode shape associated with the natural frequency omega 1, and this is the second mode shape that is associated with the natural frequency omega 2. Okay, so this is what we want to have, and these are the steps of solution that we are going to follow in order to obtain the final natural frequencies and mode shapes. Okay, I hope that you can understand well what are the things that we need and how we can obtain them. For the mode shapes, as I said, this is the equation that is going to be used. Also, I have explained it in detail in the previous video. Go and visit the previous video, please, in order to understand it. From here, you are going to find that the left-hand side is going to be equated with the right-hand side, which is a vector of 0. And you are going to find that different equations that is going to be we are going to find, for example, several equations. These equations, we are going to find that they are dependent, not independent. Means that we can find one of them is a multiple of the other. And based on that, we are not going to obtain A1 and A2 as absolute values. Rather, we are going to obtain A1 and A2 as ratios. So that's the issue here that we are going to have. We are dealing with ratios, not absolute values. What is the reason for this? As I said, because this equation, the nature of this equation, that it provides for us dependent, okay, dependent equations, the number of independent equations is 1 less than the number of unknowns, which are A1 and A2 in this case. Okay, now we understood now, and we can go more now. Okay, let's go. So let's go with the step 1. So we are having step 1, which is stiffness matrix and M. Let's go with the obtaining this stiffness matrix and and the mass matrix. Okay, first of all, we need to understand that story stiffness is represented as fixed column. This is number 1. Whenever we are looking to our system, we have like 2-story, right? And we said that we have very strong, or the girders are rigid. And at the bottom, we found that it is the columns are fixed at bottoms, right? But if we get closer to one column, we're going to find that the bottom is fixed, and because it is attached to a very rigid girder, then we can assume that here also it is fixed. So we have fixed condition, right? This means that the stiffness of the story stiffness, is going to be the case of fixed condition, which is going to be, do you remember, if we have a fixed condition, as you can see here, and we have a displacement, unit displacement at the top, so what is going to happen here? Exactly. There is a kind of shear that is going to be developed. Shear is going to be developed. This shear, the value or the magnitude of the shear, we can obtain it from the properties of the column and the end conditions. So we can say that if it's fixed, then we have this nice equation or formula, which is 12 times the material Young's modulus of this column times the inertia of it over the length of it. So this is going to give us the story shear. Again, what is the meaning of the story shear? It is the shear, the story shear stiffness. Means that it is how much force is going to be developed at the top, okay, of the column or bottom of the column. Shear. It is not flex or shear. I'm talking about shear. If we move one end, if we move one end by a unit displacement, okay, then this story shear or story stiffness, both are synonyms, okay? Whenever I say story shear or story stiffness, they are the same, okay? It equals 12 EI over L to the power 3. Okay, again, we know E because already it's given for us, right? So this is 12, this is E, 20,000, and we have I. What is I? It is the inertia of the columns here. Fortunately, in our example, they said that both columns can be represented by exactly a cross-section of 0.5 by 0.5. This means that our inertia for this cross-section is going to be 0.5 times 0.5 to the power 3 over 12. And this gives us this value, which is 5.2 times 10 to the power minus 3 meter to the power 4. We're talking about, or we are using meter units here. Okay, so now this is number 1, which is the story stiffness. We could obtain it and get it from the end condition of the column at each story and the length and the inertia of the column. And then when we are going to apply in our formula, then we are going to obtain this I. We're going to put it here, and the length is going to be 3 meters to the power 3 here. Then we're going to obtain this value. Okay, we're going to obtain this value. Okay, what is this value is all about? Okay, so this value is, what is the meaning of this? 46.29. We want the significance. As I said many times, we need to understand everything that we're doing in order to make it easy for you to understand the whole picture of what you are doing. This 46.2, it is the shear stiffness of the story. It means that if I want to move this story or the girder, if I want to move it by unit displacement equal to 1 meter, then I need force equal to 46.29 kilonewton. This is the meaning of 46.29. And this is the meaning of, as you can see here, this is the meaning of the kilonewton per meter. This means that we need 46.29 kilonewton in order to move the girder or to move the whole story by 1 unit. Okay, that's the meaning of it. Okay, up till now we understand now. I think that we understand what we are talking about. Okay. Now let's go and see the next part, which is the masses in floors. So here we have the mass, okay, on each floor will be, it is going to be mass, which is m, equals to weight over the gravitational acceleration. The weight is already given for us because we have 30 kilonewton per meter times 4, which is the span of the floor, over 9.81, which is the gravitational acceleration, meter per second square. Okay. If you substitute here, you are going to find that our mass is this value, 1224.9. What is the meaning of this? This means that we are going to have the masses, okay, is going to be lumped mass at each floor, okay, with this value. So we have the values of the masses as we can have here. Okay, and this is in kilogram mass. We're talking about kilogram mass, which means that Newton second squared over m, or over meter. Okay, so now the end of this part, which is going to be the end of the first step in our solution, is going to be related to the items that we're going to use in the stiffness matrix and mass matrix. So the story stiffness, which is K story, it is going to be 46.29, and the mass per story is going to be this value, okay, 12,244.9 kilogram mass, and this is kilonewton per meter. Then let's go and form our stiffness matrix. So let's go and form the stiffness matrix K, okay, of the entire frame. Here we are just talking about what exactly? Story, one story, but we have two stories here. Okay, this means that we need to form the stiffness matrix of the entire frame. Okay, so take care of this word entire frame. So the stiffness matrix can be determined by applying a unit displacement to each story in succession and evaluating story forces. What is the meaning of this? Okay, we're going to read it again. Let's move this. Okay, so I want to read it again. It can be determined by applying a unit displacement to each story in succession and evaluating story forces. So the meaning here is going to be given in the next slide here. If you look here, now we can generalize or put our system, the frame, to be like 2 degrees of freedom, as you can see here and as you can see here. Okay, so in this case here we are going to apply a unit displacement, at the top here at floor 2. Okay, so this is unit displacement here, as if that we are moving this point, moving in this direction, delta equal to 1 unit. Okay, and then we're going to see what are the forces that is going to be developed. Okay, what are the forces? The word forces here means that story shear or story force, they are synonyms. They are representing the same significance. Okay, so whenever that we apply the displacement here, we're going to have forces to be developed at the top and the bottom, at the first floor or at the first coordinate here, which is 1 here, floor number 1, and we're going to have forces that is going to be developed at floor 2. In a similar fashion, if we are going to apply a unit displacement at the first floor, then we're going to find that there are forces or story shears are going to be developed. The first one is going to be developed at the first story, as you can see it here in green color, and also there is another one that is going to be developed at the top mass, which is the second floor. Okay. Now let's go and see what is these kind of designation of factors that I have put here. This is K12, K22, K21, K11. What is the meaning of this? If you look here, you're going to understand it. Whenever that I have K means story shear, okay? Story shear or story force. 1, 2 means that 1, the first subscript here means stiffness. Means that I can put it like this, force. This means that force. The first subscript means force. The force that is going to be developed in this direction, which is what? Direction 1. In direction 1. How many direction or coordinates that we have? In our case, we have coordinate 1 and we have coordinate 2, right? So this is floor 1, floor 2. Degree of freedom 1, degree of freedom 2. Okay? Coordinate 1, coordinate 2. They are the same. So 1 means that the force that is going to be developed, or the stiffness that is going to be developed in this direction or in this coordinate due to unit displacement in this coordinate and this coordinate. Okay, so whenever I say K12, it means the stiffness or the force that is going to be developed in coordinate 1 due to unit displacement that is going to be applied in coordinate 2. Okay, that's the meaning here. So what if I say that it is K11? What is the meaning of it? It means the force or the stiffness that is going to be developed in coordinate 1 due to unit displacement applied in coordinate 1 too. Okay, similar, K21, the same. Okay, stiffness that is going to be developed in coordinate 2 due to unit displacement that is going to be developed in coordinate 1. Okay, now in this case we are going to put what? If we have like 3, 4 coordinates, this means that we are going to start to put the unit displacement here and see what are the forces that is going to be developed in other degrees of freedom. And then we're going to make a unit displacement in the second coordinate and see what are the forces that is going to be developed in the other degrees of freedom, and so on and so forth for all of them. Okay. Okay, I hope that you can understand what I'm saying up till now, and I hope that it goes well with you. Okay. Now this is going to give us a very good exposure to what we should or how we are going to form our stiffness matrix. First of all, we understand that the stiffness matrix is 2 by 2 because we have 2 degrees of freedom, right? So we are going to form it in this way, and as you know, we're going to put it based on the number of columns, and so the subscripts here is going to be put as K11, which means that row number 1 and column number 1. So the first subscript gives or provides the row number, and the second subscript gives the column number. Okay, so K12 here, K21, K22. You're going to ask me, this is row and column. Does it have any relation with what we have explained here? The answer is yes. So you are going to understand it in a minute. Now I'm going to explain this point because it's very nice and showing to us that what is the meaning or the significance of the stiffness matrix coefficient. If you do not understand this point, please pause the video and revisit the previous video. I talked about stiffness matrix or the stiffness coefficient, and I mentioned about this, and I mentioned about this rule. Okay, so we're going to find it in detail in the previous video. Okay, Okay, then we are going to equate it. K11 is going to equal 2K here, and K12 is going to be minus K, and K21 is going to be minus K here, and K22 is going to be K. You might ask me from where we got this, how we can obtain 2K and minus K and K. Bear with me for 2 minutes and I'm going to return back to this and you're going to understand it fully. Okay? Okay. There is an important hint that is going to help us to understand this, like this analogy, that think about the applied displacement as an action and the other developed shear forces, means that the shear stiffnesses, as reactions. Okay, so the meaning is here we are going to apply unit displacement at floor 1, right? So we are going to call that K11, and this is understandable. We understand it. The force that is going to be developed in the direction of the applied displacement at the same coordinate is going to be K11. It is K11, means that it is stiffness in coordinate 1 due to displacement in coordinate 1. And this is the right thing. The green arrow here means the stiffness, the shear that is going to be developed at coordinate 1 due to unit displacement applied at coordinate 1. That's very nice. How much this one? If you look here, how much this K11 from your own point of view? Let's assume that the right hand side is going to be positive, left hand side, or if it's going to the right, it is positive, going to the left or directing to the left, it is negative. Can you consider that we are making one displacement at coordinate 1? How many columns are resisting this displacement? Exactly. The top column and the bottom column. Then the shear stiffness that we have explained before or obtained before that is going to be resisting this displacement is going to be two of them. And because we have the top floor and the first floor, they are having the same shear stiffness, this means that K11 is going to be K of the first story plus K of the second story, which means that 2K, right? Look here, this is 2K. And this is right, K11 is 2K. They are, or the displacement at coordinate 1 is going to induce resisting force that equals to the shear stiffness from the bottom column plus the shear stiffness from the top column, which is going to be K1 plus K1 plus K2, floor 1 and floor 2. But actually in our case, floor 1 and floor 2, they are the same. So it is 2K here. That's the meaning of K11 equals 2K. Okay. Now let's go to this point here. Again, we want to know what is the shear force that is going to be developed at the second floor due to the application of unit displacement at the first floor, right? We're going to call it K21, right? Stiffness at floor 2 or coordinate 2 due to unit displacement at coordinate 1. What do you think about this? Exactly. It is going to be resistance of one column only. So it is going to be only 1K, which is the K of the second floor. And it is going to be in this direction, which is the left direction. And here comes the importance of the hint that I have mentioned to you. Think about the applied displacement as an action. So as if there is an action here. So K11 is going to be positive. It is going to be positive. However, K21 is going to be like as if it is like resisting. We need to have like resistance here. Okay, we need to have resistance. So here, for example, we need to have another like K, for example. So we have K here, and we have like 2K here. Okay, then this is going to be one of like the reaction that is going to be developed, and based on that it is going to be K, and the sign is going to be minus, because we said this is going to be minus. I want to clear up everything here. So here K21 is going to be K because of the direction of the arrow, as we can see. As I said, if this is K22, which equals to 2K, it would have two resistance, one from the top and another one from the bottom that we do not care about it, but it equals K also. Okay. So in this case, we are going to find K21 to be K magnitude and minus with sign. So K21 is going to be K in magnitude and minus in sign. Okay, now let's go to the next part. We finished now this the displacement at coordinate 1. Let's go to the displacement, applying displacement at coordinate 2. So we're going to apply this displacement here. It is unit displacement, delta equal 1. Applied unit displacement at coordinate 2. Then, as we said, in the direction of displacement, assume that the stiffness here is going to be as action. It is going to be K22, right? K2 stiffness at coordinate 2 due to displacement at unit 2. So here, what is the resistance here? It is the resistance of one column only, right? The resistance of one column. So in this case, we are going to have the K22 equal to K. And what is the sign of it? It is going to be positive. So K22 is going to be K. And as you can see here, it is positive. Okay? Okay. Now let's go to the next part, which is related to what is the stiffness that is going to be developed here. It is going to be K12, which means that the stiffness at coordinate 1 due to displacement at coordinate 2. From here, as you can see from equilibrium, we need to have the green arrow at coordinate 1 to be in this direction, which is negative direction. I mean that directing to the left. This means that Q12 should equal to exactly negative, because it is directing or heading to the left, and the magnitude is going to be K. Okay. Did you understand this? I'm sure that it might be difficult to some extent, but if you look deeper, you're going to find it's clearly simple, very simple. Okay. Just if you couldn't understand it, pause the video and repeat what I have said again, or listen to what I have said again, and you're going to find it pretty easy. This very simple concept that I am explaining here, if you could understand it in this example, you can apply it in any different type of multi-degree freedom system, whether it is 3, 4, or more, because they are applying the same concept exactly. So if you could understand what I'm saying now, this means that you have understood the multi-degree freedom system, how the stiffness matrix works, okay, or formulated. Okay, that's very good. Let's go to the next part, which is related to the mass matrix. Now, still we are under the first step, which is related to the mass matrix and stiffness matrix. Okay. Now, as you can see, the mass matrix, it is 2 by 2 mass, and it's actually simple to be formulated, because we have said that before in the previous video. It is diagonal matrix, okay, means that the off-diagonal elements are 0. So it is easy for us. And we know M already, it is known for us because we have calculated it before. Okay. Now let's go and understand more about the formulation of the equation of motion. Okay. This is only like something redundant. No need for us to make this, because if we have formulated the stiffness matrix, in the previous slide I have done it, and we have the mass matrix as we have obtained it here, then it's okay. We can go directly and work. But I want you to know that this formed stiffness matrix and mass matrix, they are representative of the equation of motions. the equation of motion that we need to formulate. So now it is, as I said, no need to make this a step, but it's only for your understanding. So now we are going to put our mass, which is here, this is the mass 1, here it is mass 2, because as I said, we have like two masses. This is M1, M2, and we said that we can formulate it to be mathematical model and then free body diagram. Please revisit the previous video to understand what is the meaning of mathematical model and what is the meaning of the free body diagram for each mass. Now I'm putting the free body diagram of each mass. The first mass is going to have inertia forces, okay, is going to have inertia forces, which is M1 U1 double dot, and there is some resistance here, which is K1 U1, elastic resistance, and between the two, the mass 1 and mass 2, is going to have K2 times U2 minus U1, and at the same time we're going to have for mass 2 we have the inertia forces, right? We have the inertia forces, which is M2 times U2 double dot. Then if we're going to apply the equation of motion for the first mass, we can put it like M1 U1 double dot plus the resistance, which is going to be K1 U1 minus K2, this is the force here, K2 times U2 minus U1 equal to 0. It should be in under equilibrium. This is the equation of motion for mass 1. For mass 2, we have only two forces being applied there, M2 U2 double dot plus K2 times U2 minus U1 equal to 0. And this is the equation of motion for M2, right? So this is what we are having here. Okay. Okay, so in this case, we are going to arrange this equation of motion. We're going to arrange this equation of motion for each mass. We're going to put them in a matrix form. So we're going to put it in a matrix form. We're going to put it in a matrix form. So in a matrix form, we need to put equations. So the first equation, the first row in this matrix, stiffness matrix, times U1 and U2, which is the vector here, right? It is going to give us the equation of motion. So in this case, so in a matrix form, what I mean here that we have like in matrix form, we need to have the mass matrix, we need to have the stiffness matrix and the vector of displacement and the zero vector here. So we are going to have for mass matrix, okay, we need to have it something like this M1, 0, 0, and M2 here. And this is actually M1 and M2, they are the same M. So there is no equal here. This is only I'm putting the stiffness, or we can say the matrix form of the stiffness. And this is the displacement vector. This is the zero vector, okay, which is the vector of 0. And this is the mass, okay, mass matrix that we are needing it. And this is the first part of the equation, the first step in the strategy of our solution. Okay, so we determined now, or we have now K matrix, we have, or we are waiting for the U vector, which is the displacement. We have the 0, which is considered to be like the forces being applied in the system. We have 0, and we have the matrix of masses, or mass matrix, which is going to, these matrices and vectors are going to provide for us the second step in our solution, which is going to be related to the determinant and obtaining the frequencies, as we are going to see shortly. Okay, now let's go and see the second step. Okay, the second step here is related, as I said, to obtaining omega 1 and omega 2, the natural frequencies of our system, the natural frequencies of our system. We are going to find that the determinant of the stiffness matrix minus omega squared times mass matrix should equal to 0. From where we got this, please revisit the previous video. Okay, this means that the determinant here, is going to be K, which is the stiffness matrix, minus omega squared. Still here we are using omega without omega 1 or omega 2. It is only omega squared, because after that we are going to solve it to get omega 1 and omega 2 as the roots of the polynomial or the quadratic equation. But anyway, the time being we are dealing with omega only. So we have here stiffness matrix, we have here omega squared, we have here the mass matrix. Then we're going to give or provide the determinant. The determinant is going to be generally 2k. First item here is going to be 2k minus omega squared m, and this element is going to be minus k, and this element here is going to be minus k as well, because omega squared is multiplied by 0. And here this element is going to be k minus omega squared m. Okay, the determinant of this matrix is going to be obtained by multiplication of the diagonals, subtracting the diagonals multiplication. So we're going to have 2k minus omega squared m times k minus omega squared m. Okay, this diagonal minus k to the power 2. Okay, if we're going to rearrange it, then you're going to find that you have a quadratic equation in omega squared. Quadratic equation in omega squared. Take care, it's not in omega, it is in omega squared. So we are having like m squared times omega squared to the power 2 minus 3km times omega squared plus k to the power 2, okay, equal to 0. Okay, equal to 0. If you look to here, this is the left hand side equal to 0, and this is considered to be a quadratic equation. Okay, so this quadratic equation in omega squared, we can solve it. Let's see how we can solve. Okay, so we can solve it, as you can see, using the law or the quadratic equation solving, which is the law of solution x1 and x2 equal to minus b plus or minus square root of b squared minus 4ac over 2a. And you know, of course, what is a, b, and c. It is related to the coefficient of the omega squared to the power 2 and omega squared only, and the absolute term. Okay, so I think that you are familiar with this better than me and you understand it very well. Based on that, if we're going to solve our equation, you are going to find that we have omega 1 and omega 2, the roots. So omega squared is going to have omega 1 and omega 2. Now we have two roots because we have 2 degrees of freedom. We are going to have 2 different roots. The first root is 0.038 rad per second, and the second is going to be 0.099 rad per second. Okay, so these are the 2 roots, and they are the natural frequencies. Okay, natural frequencies of what? They are natural frequencies of the mode shapes that I'm going to get in the next step. Okay, do you remember when I was saying that we have different ways, okay, of representing the shapes of the system? So this system is going to work with, or this mode shape is going to displaced with this omega. It will go back and forth with omega. I'm going to talk about this in detail toward the end of the presentation. Okay, And omega 2 is going to be with the second mode shape, which is, for example, is going to be something like this. Okay, so our mode shape is going to be associated with omega 2, and we are going to have this kind of frequency of it. Okay. Okay, now this is the second step, and we now obtained omega 1 and omega 2. Let's go to the third step in our strategy of the solution. Okay, let's go to the third step. Okay. Step number 3 is going to be related to the mode shape. It is going to be related to mode shapes. And remember, last video we were talking about this equation. From this equation we can obtain or get the ratios of the mode shapes that we have. We have two mode shapes, right? We have two mode shapes, A1 and A2. Okay, every one of it is going to have like A1 and A2, right? Amplitude for the first floor, amplitude at the second floor. Okay, so that's the issue here. When we look to the mode shape equation here, as we have explained in the previous video, we derived this equation and we understood well what is this equation is all about. So it is going to be the matrix of the stiffness matrix times omega squared m times the mode shape, which is the amplitude vector, equals to the zero vector here. Okay. The problem is this equation, we have omega here, right? But omega, we have actually two types of omega. We have omega 1 and we have omega 2, right? So we are going to repeat the solution of this equation two times, or we are going to substitute with omega 1 and omega 2 in this equation, and we are going to obtain two different A. So A is going to be A1, A2, which is going to be associated with omega 1, and we are going to have also another A1 and A2. Okay, they are totally different but associated with omega 2. So we're going to have two different mode shapes. Why? Because we have two different frequencies. When we substitute in this equation, we're going to find that we have two different mode shapes from here. Okay, so based on that, let's go and use the first root, which is omega 1, and substitute in this equation. Okay, and substitute in this equation. We have 2k minus omega 1 squared m. This is in the first term here. If you are going to put this equation, you're going to find after substitution that you are having, this is a matrix. Okay, this is a matrix. Okay, and this matrix, because this is minus, so this matrix is going to be multiplied by this vector, and then they should equal to this vector, right? So here we have like 2 by 2, here it is going 2 by 1. This means that we are having here 2 rows by 1 column, right? Okay, so in this way we're going to put k minus omega squared m. One time we'll put it omega 1, another time we'll put it omega 2. Now let's go with omega 1. So the first term here is going to be 2k minus omega 1 squared m. And here it is going to be minus k. Remember that m is diagonal matrix, so we have off diagonals are zeros. So we are having minus k here. Similarly, for this coefficient is going to be minus k. And for the last one here, it is going to be k minus omega 1 squared m multiplied by a, which is going to be a1 and a2. Remember that it is associated with omega 1 in this case, equal to the right hand side is going to be 0. Okay, we know everything here. Okay, numerically, we know k, we know omega 1, we know m. Everything is known, okay, from the previous slide. So we know k, we know omega 1, we know m, which is the masses, okay, the mass of the floors, omega 1 natural frequency associated with the first mode, K, which is the story shear, story stiffness. Everything is known, so we can obtain these terms easily in the matrix, right? It is going to be numerically going to be like this. Please verify these numbers, okay, by yourself. You can check it. If there is any mistake, please comment on the video if there is anything not right here, okay? And after that, we are going to equate it. It is going to be multiplied by A1 and A2, right? And equal to 0. Then we're going to use these to obtain the equation. So we're going to obtain or multiply 74.9 times A1 minus 46.29 times A2, and it equals to 0, right? Similarly also for the second row here, minus 46.29 times A1 plus 28.6 times A2 equal to 0. These are two equations, right? That's very true, and let's see how it will work for us. When we are going to work for this, we're going to find the first equation is 74.95 times A1 minus 46.29 times A2, is 1 times A2 equal to 0, right? Okay, similarly for the second row here, we're going to have this. Look to this equation. Without anything, just look to these two equations. I want you to look to these equations. Do you think that there's something unique about them? I guess yes. There is something here. Try to multiply the second equation by 1.6, for example, and let us see what will happen. You're going to find that if you multiply the second equation by minus 1.6, it would give you the first equation. This is the meaning of dependent equations or coupled equation. Means that actually they are not two equations. They are one equation but repeated with different factors, okay? Multiplication. So I can, for example, I can say there is another, if I want to like confuse you, I'm going to say that, well, we have another third equation. I'm going to multiply equation number 2 by 2. So it is something here times A1 plus another thing times A2 equal to 0. And I'm going to claim this is the third equation. Actually, it is not a third equation. This is only a multiplication of one of the equations. So it does not work for us. It will not add anything for me. This is what we call it, that the number of equations, 1, 2, is less the real number of equation. We call it independent. Okay, independent means that independent equations, they are dependent equation here. So the number of independent equations is one less than the number of unknowns. How many unknowns do we have here? A1 and A2. So this means that the number of unknowns, 2, which is A1 and A2, the number of independent, take care of this, independent equation is 1, not 2. Okay? Because as I said, if you multiply here by 1.6, it would give you the first equation. So it is not an equation actually. The second equation is not an equation. It's a repetition of the first equation. Okay? So this makes a problem for us. What is the problem? That the problem is that we cannot obtain A1 and A2 in terms of absolute values. We are going to obtain ratio between A1 and A2. That's the maximum that we can obtain. Okay? Okay. So based on that, we're going to deal with the situation here. And we're going to claim, well, if this is the case, then we're going to say this means, this is just a note here, this means that the equations are dependent on one another. For example, one equation is a multiple of the other. In our case, equation 1 equals to minus 1.6 equation 2. You can check it by yourself if you want. Okay? So this makes the absolute values of the unknowns cannot be obtained. Okay? The absolute values cannot be obtained because we have, as we said, the number of equations are one less than the number of unknowns. Only the ratio that is going to be obtained can be obtained, A1 over A2. So we can choose any equation, and from here we can obtain the ratio A1 over A2. It is going to be, for example, here it is going to be 46.29 over 74.95, and this would equal 0.6, which means that it is the ratio of 0.6 over 1, as if A1 is 0.6 and A2 is 1. Okay, so we can obtain only the ratio. From these grade 2 equations we can obtain the ratio. Okay, you understand up till now? I hope that everything is clear for you, and I hope that you can get through what I'm saying easily. This means that the first mode shape ratio is A1 over A2 equals to 0.6 over 1. This is the graphical representation of first mode. This means that if we assume that A2, which is the amplitude of displacement at the second floor, is going to be 1, this means that the amplitude of the first floor is going to be 0.6. And the mode shape of the first mode shape, which is related with omega 1, okay, we call it the first one. The first here always related with the least frequency. Okay, this was the least frequency. We call it the first, which is associated with the longest period. Okay, so we have here 0.6 and 1. This is what we call it the first mode shape, the first mode, or the first normal mode. It is going to be 0.6 and 1. So if you are going to ask me, does it mean that A1 equal to 0.6 and A2 equal to 1? The answer is no. So they are, A1 does not equal 0.6, A2 does not equal to 1. It is the ratio. This means that A1 could be 1.2 and A2 could be 2. Okay? It is the ratio between the two. It does not mean the value itself. Okay, so that's the meaning that we need to bear in our mind regarding this issue. Okay. Okay, so now let's go to the next part, which is related to the application of omega 2 and repeating the same procedure again. So here we are having the second root, which is omega 2. We're going to follow the same way that we have used before. So we're going to put the same 2k minus omega 2 here. Okay, squared m, and here it is k minus omega 2. Okay, squared m, and minus k the same. A1 and A2, they are associated with W or omega 2. This means that they are different. This is the mode shapes for omega 2 equal to 0. In a similar fashion, we're going to obtain the numerical values, okay, and then we're going to have the same coupled equation, dependent equation. So the same applies here, and we are going to obtain one equation only. In this case, I only used one equation here. So we have A1 here, A2 here, and these are the terms or the numerical values associated with A1 and A2. And I found that A1 over A2 equal to minus 1.68. It means that as if the ratio between A1 to A2, as if it equals to minus 1.68. As A1 equal to minus 1.68, as you can see here, and A2 equals to 1. Take care of the value here and the minus. So if we say that going to the right is positive and going to the left is negative, this is the sign convention. So if we say that A1 sorry, this is, yes, this is A1, yes, that's right. So if A1 equals to minus 1.68, this means that it is going to be to the left by 1.68. And A2, which is 1, it is going to be the right. So the deformed shape is going to be like, as you can see here. Okay, as you can see here, they are different than the first mode. Okay, if you want to recall what we have in the first mode, this is the first mode and this is the second one. They are totally different. Okay, here the two masses are going into the same direction, which is the positive direction, for example. However, here in our case it is not. We have the one mass going to the right, another mass is going to the left, because we have minus here. The ratio is including minus. Okay, so the minus is important in the ratio for the mode shapes. If we have minus, means that the masses are going to be opposite to one another. They are going to go in different direction. This means that the mass is going to go to the right, if we're talking about the second floor, while that the first floor is going to the left. It is something like this. So it is, the structure is going to have something like this. Okay. Okay. So I hope that we can understand up till now. And then let's go with the second mode shape. So now our second mode shape is going to be minus 1.68 and 1. Again, if I ask you, this means that A1 equals to this value and A2 equal to this value, the answer is no. It is only the ratio. Okay, it is only the ratio. Now we can conclude with that. Here we have first mode shape. The first mode shape is 0.6 and 1 with omega 1 equal to 0.038. Remember, this is 1, omega 1, the least value of omegas. It is less than omega 2, which is 0.099. Okay, because this is, we call it the natural frequency, or the first natural frequency, circular frequency. Okay, and the corresponding T1, which is the T here, the natural period that is going to be taken in order for this mode shape to like go in this direction and go back to the neutral position and then go to the opposite direction. T is going to be with this time. It's very large here, but anyway, this is how the numbers like go with us or went with us. Okay. Okay, so this is the shape of the mode shape here. Okay, coordinate 1, 0.6, coordinate 2, 1. This is the ratio. Okay, this is the first mode associated with it. And for the second mode, we are having, this is the second mode here, which is minus 1.63, as you can see, to the left, and 1, which is going to be to the right. And omega 2, this is the value of it. T2, it is 63.4 seconds. And the second mode shape here, as we said, it is going to be minus 1.63, I think. It is 3 here, and 1. Okay, understood? I hope that everything is clear for us. We are about to finish, so do not worry and bear with me for the remaining part. Okay, okay. Now let's go now to the notes about the example so that we are going to understand more about what we have explained here. First of all, I want to give definition for the mode shape. I want to give a definition for the mode shape. So the mode shape definition can be defined as the possible, simple, harmonic motions of the structure which can take place in such a way that all masses, take care of this word, all masses move in phase, take care of this word, in phase, in the same frequency, either omega 1 or omega 2. Okay, take care of some keywords here. We're talking about simple harmonic motion. We're talking about all masses. We're talking about in phase. Okay, three main concepts in the definition. I want you to remember them well in this definition. Simple harmonic, all masses, in phase. These are the three keywords here. Well, how we can represent this graphically? So we can go here. Let's go with the mode shape number 1. In mode shape number 1, as you can see, so if we say that this is how the motion is going to be represented, okay, it is a simple harmonic motion. The horizontal line represents t, the vertical line represents u of t, which is the dynamic response at any time. Okay. If we start at point 1, which is 0 initial condition, what will happen? What will happen? Our system, this is the point 1. Our system was in the equilibrium position. When it goes to point 2, okay, then it is going to the right with the values that we have explained before, 0.6 and 1, right? It was 0.6 here as far as I remember and 1 here. And then when it goes to 0.3, so starts with 0.1, then go to 0.2, so it is going to be like this. And then from 0.2 it is going back to position 3. This is position 3. It is going to be equilibrium. Yes, that's right. No response. It is 0. So here this is no response, equilibrium position. And then in the same time it is going to, after that, to 0.4. From 3 it goes to 0.4. This is 0.4. It is going to the left, 0.6 at coordinate 1, 1 at coordinate 2, right? So from 3 it goes to 4, 0.4, the maximum. This is the maximum. And then it will go back again to the equilibrium position, 5. From 4 it goes to 5. This is considered to be complete cycle, T1. This is T1. So we are going to be here again, equilibrium position. So we are going to back again to 5. So the system is going to be stand still again. Okay. This is the mode shape number 1 with the frequency that we were talking about, omega 1. So this shape is going to be repeated over and over again under, and it takes time, T1 in this case. Okay. Important note here is both floors reach their maximum displacement at the same time and pass through the equilibrium position at the same time. This means what? If the system, this is the masses here, okay, they are going to reach here and here in the same time. This is 1, for example, this is 0.6, right? But this would be faster than this to reach at the same time of the other mass. If this is mass 1 and mass 2, so in the same time after, for example, here, let's assume this is, for example, 0.1 second, for example. Okay, so after 0.1 second, mass 1 would be here, mass 2 would be here in the same time. And then when they are going back to the maximum amplitude to the left, they are going to pass through the equilibrium position in the same time. Okay, so that's very important concept, and this is an important hint here, because they are working under what? The same circular frequency, natural frequency. Okay, that's an important issue for the mode shape, for the mode shape. Okay. Okay. Now let's go to the mode shape number 2. Okay, this is mode shape number 2. So what will happen here? Again, t versus u of t, and we have 0.1, 2, 3, 4, 5. And the complete cycle it takes time t2, which is related to the natural frequency omega 2. And these are the points 1, 2, 3, 4, and 5, right? It is similar to what we have explained before. In 1, there is nothing. This is equilibrium position. This is 0. Number 2, it is going to be, as we said here, it is minus 1.68. Here it is going to be 1, right? And then we are going to 0.3. So we're going to 0.3 here, which is equilibrium position. That's right. We do not have any displacement here, or the dynamic response is going to be 0, right? And after that, from 3 to 4, we are going to have the maximum amplitude at the opposite side. Here it is going to be 1.68. Here it is going to be minus 1. I mean that the amplitude is the same maximum, but in different directions. And then from 4 it's going to 5 again. So we're going to have the equilibrium position again. Okay. So this is, as you can see here, these are the masses. They are moving in the same time. They are reaching the maximum amplitude at the same time and passing through the equilibrium position in the same time. Okay, so this is the meaning of the frequency and the representation of the frequencies. Okay, and after that we are having another hint for the example. The first mode is associated with the lowest omega, and this is right, okay, or maximum t. So this is what we call it, the maximum t, or the lowest omega circular frequency. The other modes called higher mode shapes. So like we have omega 1, this is the natural circular frequency. Omega 2 or omega 3 or omega 4, if we have more degrees of freedom, we call them higher mode effect or higher mode shapes. Okay. The next hint is related to the dynamic characteristics depend only on mass and stiffness. This means that no damping. Why? If I ask you why we do not have damping here, because as we said before, damping is going to have negligible effect on buildings, as we mentioned, and they are not going to change the natural or dynamic characteristics. Okay, so mass and stiffness, they are having the greatest effect. Okay, unless that we have additional or additional damping or something, this is might change the effects, but in general the natural dynamic characteristics of any building, if we're talking about buildings, contribution of damping is minimal. Okay, and then I'm going to give some examples here related to the mode shapes. Okay, this is, you can find it in Humor book chapter 10. Just the representation is very nice actually, so I decided to show it to you here. So as you can see, we have like 2 floors, okay, regardless of the masses here. Masses is doubled here. We have U1 and U2. Then we have, as I was explaining, 1, 2, 3, 4, 5, and it is explained here for each floor. So for floor 1, this is the dynamic response based on U1. We have 1, 2, 3, 4. As you can see that we have a complete cycle here, starting from 1, okay, maximum, going to 2, a little bit less, then 3, no response, which is neutral position, and then 4 and 5, it is going to be repeated in the other direction. As we can see, this is going to be this this circle, we call this circle the rotating vector representation. It is the maximum amplitude here because the amplitude of U2 is higher than U1. So it has like vector representation here. The diameter of the circle here is small and the diameter here is larger. Why? Because we have here, this is the amplitude, the maximum amplitude, which is the diameter here for U2, which is the top floor or the second floor. Here the amplitude is small, then the diameter of this circle is small. Okay, and as you can see, it is T here. Okay, and another nice one, which is the opposite, or we can say that it is the response of two-story frame in the second mode. So this is the second mode. Similar to us also, it is like 1, 2, this is 1, and this is a little bit 2, this is 1, 2, 3, 4 after that. 3, it is the neutral position, which is 3 here. And then 4 and 5, it is the opposite of it, in the opposite direction. And then repeat again, the same, repeat again, and so on. So we have this for U1, and this is going to be for U2. Okay, that's the how the displacement is going to be. This is the frame. This is the displaced shape, as we said, of the columns, for example. This is the rotating vector representation, and here we have the displacement time history. We call the displacement time history. Okay, and the last one, maybe we have, if we have like 2 degrees of freedom, this is a case, a very nice case, where that we are having response of two-story frame subject to arbitrary initial condition. Arbitrary initial condition. It seems that the initial condition here at 0 time, t equal to 0, it was like shifted, as you can see here. This is 1 here, which is the initial condition. Then the structure is going to respond based on the initial conditions here, and we are going to find that also this is 2, for example, which is this point, and then this is 3 here, which is this point, and then 4. We cannot get where exactly 0, because it will not get through this equilibrium position exactly, but anyway, 4 and 5, they are represented here, and this displaced shape of the column, and this is the displacement or the time history, displacement time history. The next one, and maybe the last one, it is the 3-degree freedom, just to let you see the meaning of this. If we have 3-degree freedom, the same story that we have mentioned before, it is going to apply here. This is the mode shapes of 3-story shear frame. This is the frame itself. This is the first mode. The first mode always, all masses are going into the same direction. So here, this is the mass, here. They are going into the same direction. Okay. However, for the second and third, you're going to find that some masses, they are going into one direction. Other masses, they are like going to different direction. This means that the masses, they are as if they are canceling one another. This is why always you're going to find the first mode is going to contribute to the mode, the total shape of the structure under motion. Why? Because all masses are going to be in the same direction. So this makes the modal participating mass ratio to be higher, or the highest for the first mode. Here you're going to find some masses right, other left, some right, other left, and so on. So they're going to cancel one another, and the total contribution of this mode shape is going to be less than the first mode shape. This brings us to the end of this video. Thank you very much, and it is very important example that is going to give you a very good explanation for multi-degree freedom system. Please pause the video at any time and try to think about every explanation that I have said. And thank you, and see you in the next video.